Hello everyone, I'm Gang Changzhou from Sun Yat-sen University, and I'm the presenter of our paper Vibra Neuroadaptive Streaming of VBR-encoded Videos. This is the outline of my presentation. Firstly, the characteristics of VBR video encoding and CBR video encoding is compared. Then the challenges and problem formulation of VBR-encoded video streaming are presented. Next, the design of Vibra and the evaluation results are introduced. As we all know, a video can be compressed using two main encoding schemes, constant bitrate, namely CBR, and variable bitrate, namely VBR encoding. Under CBR encoding, the simple scenes and complex scenes are encoded with the same bit budget. In contrast, VBR encoding allocates more bits to complex scenes and fewer bits to simple scenes, to guarantee consistent video quality across different scenes. VBR encoding yields higher video quality than CBR under the same average bitrate, or the same video quality but with much less average bitrate than that of CBR. However, the size of different video chunks in VBR-encoded video fluctuates sharply, while in the CBR-encoded video, the chunk size is relatively fixed. As we can see in this figure, the red line means the chunk size variation of VBR-encoded video. It ranges from 635 kilobytes to 7.6 million bytes in our measurements. The design of effective ABR algorithms for VBR-encoded videos faces a number of challenges. First, the variance of chunk size together with bandwidth dynamics makes it difficult to perform optimal bitrate selection. Second, the phenomenon of rebuffering occurs more frequently for VBR-encoded videos compared with CBR-encoded videos. The ABR algorithm should be deliberately designed to avoid exhausting the playback buffer and causing playback freezing. Third, the ABR algorithm for VBR-encoded videos needs to take extra influential factors into account, such as chunk size and chunk complexity, which have cascading effects on the downloading of subsequent video chunks. The illustration of download process can be seen in this figure. A video chunk, for example chunk I, is fetched by the client player at time ti, and the duration of its download process is tdi. If the buffer is exhausted during this download process, the rebuffering event occurs. After the video chunk has been completely downloaded, the buffer size increases p seconds, which is the length of a video chunk. The QoE metric of user can be defined as video quality minus smoothness penalty minus rebuffering penalty. As shown in this equation, the first term denotes the sum of video quality perceived by a user for all m chunks. The second term is the smoothness penalty associated with the quality variance of video chunks. And the last term is the rebuffering penalty. Our goal is to maximize users' QoE through making bitrate selection for each video chunk. As the problem is NP hard, we propose Vibra to find a near optimal solution. The overview of Vibra can be seen in this figure. At the beginning of video playing, the chunk download finishes the first video chunk in the default bitrate. The finished video chunk is sent to playback buffer and can be played by the video player. During this process, the video and network information and the buffer occupancy are observed by the state observer. Then the state of the next video chunk is sent to the bitrate scheduler for bitrate selection. Next, the state, the bitrate selection, and the reward of each video chunk will be the inputs of the model channel. This information is used to train ABR algorithm through A3C model. The state space of Vibra includes the average throughput and the download time of past several video chunks, the size of next video chunk, the buffer occupancy, the bitrate of last video chunk, the number of left chunks, the quality level of next several video chunks, and the value of rush flag. The state is sent to two neural networks, namely actor network and critical network. The actor network represents the policy of an agent, and the critical network is used to evaluate that policy. Finally, an action from the action space is generated by the policy according to the state. The chunk size in the state space is the exact size of the next video chunk, which contains the size of chunks with different resolutions. The quality level of a video chunk is calculated by its relatively chunk size. In the state space, the quality level can indicate the complexity of video chunk and measure the dynamics of chunk sizes for the next F video chunks. Moreover, according to our measurements, we find that the client is conservative in the final stage of VBR streaming. Even the duration of buffered content is longer than the duration of the remaining video chunks to be fetched. It is actually desirable to fetch video chunks with higher bitrate to further improve users' QoE, without causing the occurrence of rebuffering events. Therefore, we use rush flag to be a condition indicator to check whether the above conditions have been satisfied. To evaluate the performance of Vibra, we conduct extensive trace-driven experiments, and the results show that Vibra outperforms Pensive with more than 8% improvements on both the FCC dataset and Norway dataset. Compared to CAVA, which is the most recent ABR algorithm for VBR-encoded videos, the improvements are at least 28% on both the FCC dataset and the Norway dataset. For the QoE components, the results show that Vibra performs the best in bitrate utility and rebuffering penalty. That's it. Thanks for your listening.